Hello everyone and welcome back to Thermo Shorts, where today we're going to go through a first law problem. I won't read this all to you, but you can certainly pause and do that yourself. Essentially, we have this piston cylinder assembly that's going to go through two processes, and we're asked to find the total work, the total heat, and to sketch the TV and PV diagrams. We're also given tables like this one, which is a two-phase table that you might see on an FE exam, and also some steam tables and some properties, which you also would see on an FE exam. So we're given a bunch of information about some different states. We have two processes here, one that goes from state 1 to state 2, another that goes from state 2 to state 3. We're also given some information about the geometry of the piston, which we'll use. And what we want to be able to find is the total work, the total heat transfer, and we want to sketch the TV and PV diagrams. So here's what my schematics look like. I have this piston cylinder assembly. My first process happens at constant pressure. My second process happens at constant volume. I'm also told that the mass is constant. And because the volume is constant and the mass is constant, that means that the specific volume is also constant as we move between states 2 and state 3. If I'm looking to find the volume of state 1, I will take the mass multiplied by the specific volume of state 1, which I can get if I can fix that state. So, like all first law problems, we start by writing the first law, and this is the version of the first law that we write when we have a closed system and we're doing a problem in elapsed time format. Here, we'll first assume that we can neglect kinetic, potential, and spring energy terms so that our delta E term is dominated by the change in the internal energy. Now, we'll integrate PdV to find work. I'll get the difference between the internal energy by fixing the states and finding mass times the difference in the specific internal energy. And after I've done that, I'll be able to find the heat transfer for each process. So here, this is the process we'll use as we go between state 1 and state 2, but we'll do the same thing between state 2 and state 3, and then I can add up the work for the two different processes and the heat for the two different processes, and I'll get the total work and the total heat. This is what my state table looks like. I always like to keep these so that I'm accounting for the information that I know in a place where I can sort of be constantly moving back and forth and I don't get lost in the problem. So here's the geometry. They don't come out and tell me the volumes, but I can find the volumes if I want, particularly for state 2 and state 3, because I know L2. So here I have this equation for volume, and I can find that the volume at state 2 and the volume at state 3 is 3.14 meters cubed. Now, if I want the specific volume of state 2 and state 3, I have to divide by the mass. In this case, I can get a specific volume as well. Now I put that into my table over here in red. Now I want to figure out what phase I'm in all of these three states, because if I do that, then I can fix the states. This is my TV diagram. First, I'm going to draw a constant pressure line. I notice that the temperature at state 1 is below the saturation temperature for my given pressure. Now I know that state 1 is a subcooled liquid. State 2 exists at the same pressure, but I know the specific volume. Here, the specific volume of state 2 is less than the specific volume of the saturated vapor. So I know I'm two-phase in this case. Next, I'll draw my pressure at 4 bars because my pressure increases from state 2 to state 3. Now this part's only a sketch. I don't actually know if this 4-bar line is going to keep me under the vapor dome. But here I'm going to assume that these two lines intersect in the superheated vapor region, which I'll check when we start to fix our states. I can do a similar process on a PV diagram. So here I'm going to draw this constant temperature line of 100 degrees Celsius because that's the saturation temperature for one atmosphere. I know that my pressure here is this 1 atmosphere line, but my temperature is below 100 degrees, so this line would have to shift down. And again, state 1 is a subcooled liquid. Again, I draw my constant specific volume line that I'll travel from state 2 to state 3. I'll put state 2 down here. Then I know that state 3 happens at 4 bar, so I shift up. And again, I'm assuming that this is going to land in superheated vapor. So now I think I know the phases of all 3 of these states. Now I'm going to try to find the total work. So I know that work is the integral of PdV, so I can evaluate this as I go from state 1 to state 2, where I have a constant pressure. So I just get P times delta V, or pressure times mass times the change in specific volume. I don't know this work. I do know pressure. I know mass. I know specific volume at state 2, but not at state 1. So I need to get the specific volume for state 1. What I'll do here, because this is a subcooled liquid, but I'll assume that the specific volume is approximately equal to the specific volume of a saturated liquid at the same temperature. And I'll get a value that's about 1 over 1,000 here. I put some numbers into my calculator. Notice that I'm tracking the units in my calculation, and I'll get a value of work from state 1 to 2 in kilojoules. So I like the units here, and it's positive because my volume is expanding. Next, I want to go between state 2 and state 3. Again, I find the integral of PdV, but in this case, the volume is constant. When volume is constant, the area under this vertical line on a PV diagram is 0, and that's my work from state 2 to state 3. Next, I'm going to try to find the heat transfer. I'm manipulating the first law for both of these 2 processes, and I'm trying to see what I know and what I don't know. So what I need to do to find the heat in both of these processes is fix my states. I need my specific internal energy at state 1, 2, and 3. State 1 is a subcooled liquid. So I'll assume that the specific internal energy here is equal to the specific internal energy of the saturated liquid at the same temperature. I can go to my 2-phase steam tables here. I pick out the right value on the table, and I put that into my state table. For state 2, I know this is 2-phase, so I can use this equation for quality to find the specific internal energy. But in this case, I don't know X. So I have to turn to my known specific volume to get quality. And then once I get quality, I can use that value of quality to find my specific internal energy. Notice that the quality here is close to 1, so I get a value that should be close to Ug at this temperature. Next, I'll go to my third state, which I think is superheated vapor. Here, if it's superheated vapor, I got to look on those tables, and I need to find my interpolation factor A. Again, I know my specific internal energy, which is in between these 2 values here, so I can find my interpolation factor A and use that value to get my specific internal energy. So here, that's exactly what I do, and I find my specific internal energy, and I put that back into my state table. Now, I just have to find the heat transfer for these 2 processes, but I know all the variables, so now I'm just putting things into my calculator. I find the heat transfer between state 1 and state 2, and then I do the same between state 2 and state 3. Then I find the total heat transfer by adding these 2 numbers together to get the total heat transfer. The total work is just the work in the first process because there is no work in the second process. I have reasonable confidence in this answer. I checked my units throughout my calculations and they remained correct, so I can't show that I did anything wrong there. I only used incompressible assumptions for incompressible liquids, and my signs are what I expected because here in the work, my volume was increasing and I got positive work. So I feel pretty good about this solution.